summarize the four key stages: the conceptual, preliminary, and detailed design stages, followed by the final acceptance stage.
We were told that our spar had to withstand a point load of 2.5 times its weight, as well as being able to prevent tip deflection from exceeding 15mm. This was important in deciding which spar designs were best suited to meet the requirements.
Material analysis allowed us to identify feasibility of structures as well as possible joining methods and failure points that might occur. Initial sketches can define a project's trajectory, allow for team collaboration as well as eliminating certain designs and providing a visual output for us to make decisions.
During the conceptual design phase, it can be good to turn sketches into real-life three-dimensional prototypes by assembling foam board together. In our case, we built 3 different spars and managed to get an idea for each design's strengths and drawbacks, what folding methods were best, and the benefits of using fiber tape over hot glue to assemble ours. With the help of experimental data, conjecturing which design is most adequate can help focus efforts in the next phase. In our case, the I-beam proved to be the least compatible with our requirements, and the hexagonal spar caused problems under compression, as well as with production and testing. This left us with the cuboid spar as our first choice, although we kept studying the hexagon just in case.
Excel played a crucial role in our project during the early stages, for direct stress and deflection through second moment of area, and for torsional compliance through polar moment of area. The graph building tool allowed us to visualize bending moment distribution, showing us that the root of the spar is under the highest bending stress and should be reinforced.
CAD allowed us to save time, however, due to not testing our non-load bearing structures, we had to redesign our ribs.
In order to simplify our calculations, we made the following assumptions. The load applied entirely at the tip, ensuring accurate loading conditions. The change in extension and twisting angle was unaffected by the other types of stress that could be involved, and the support was ideal and completely rigid.
To reduce this weight, a rectangular spar is designed using several smaller rectangular sections of varying lengths. Both models were imported into SolidWorks for testing and compression in terms of stress, displacement, and strength. From the result, we found that the rectangular design performs better than the hexagonal one in many aspects.
We determined the maximum torsion force the spar could tolerate in both directions by applying a load and measuring the twisting angle. We also determined the bending stress limit by applying a load and measuring tip deflection until failure of the structure.
Our prototype met the requirements. We then began to optimize by reducing the cross-sectional area, increasing the chamfered spiral to 3 layers instead of 2. Testing gave us the idea to use double-sided tape to prevent spar separation at the base. By using our test data, we were able to adjust deviations in our simulation. This allowed each design cycle to occur faster, allowing us to build up on our previous knowledge.